Yeah, hello everyone. I'm Zhao. I'm researcher from Adobe Research. Yeah, sorry, I'm in US now. I cannot enter the workshop physically. So today I'm going to talk about some fast iterative algorithm using some new techniques which is not known in the literature and which is called like nearest neighbor or first neighbor search. And this is a joint work with a bunch of students from Rice and UT Austin and SMU. Usually, what is optimization? Optimization has two big categories. One is convex and the other is non-convex. And usually, you are given a function f, and your goal is to find parameter w, such that f of w is minimized. So what do we do in general? Is at the beginning we initialize a w0 to be some random matrix, and then after each iteration we are trying to run some greedy type of algorithm until we converge. So in today's talk, I will focus on a non-convex setting, which is about deep learning, deep neural network. So usually the running time has two parts. The first part is number of iterations, and second part is cost per iteration. The cost per iteration can be as big as input size in general. So naively, if you run an iterative algorithm, it will take at least t times n time. And the question is, can we do better? And the hope is if you only read the input once, and maybe also do some pre-processing, and then at each iteration you only pay c cost time, and eventually if c is small of n, and then ideally you will see you can solve the problem input side. So the first question is how to speed up the grid algorithm in general. So there are two ways. The first way is you just speed up the number of iterations. This will give you automatic speed up. The second way is you actually fix the number of iterations, and you are going to speed up the cost per iteration, which is the focus of today's talk. So what are our new techniques? And maybe from a number of talks in the workshop, you already see some new techniques from sketching, sampling, or maintenance. So in my talk, I will show you some new idea about how to use the furthest or nearest neighbor search to help speed up of an optimization algorithm. So I will show you a bunch of applications. The first application is how to train a neural network, and to speed up that, we will use nearest neighbor search. And this is very new work we just put on archive yesterday. So another application is for the Cartan center problem, it's very hard to solve in polynomial time, but for one side, the Cartan center is very easy to solve in polynomial time. So I will show you application use furthest neighbor, and we can actually speed up the one side Cartan center. So this paper is only in manuscript. If you are interested, you can send me email to request. There are also many applications for this technique. And for example, this technique also can be directly used in quantum setting, and also reinforcement learning, and also a famous algorithm called framework. You can use this idea to speed up. So the major idea is you want to build some data structure, and where you are given a bunch of points or images, and the question is how to process this data structure to support fast query. And also what are the queries you need to speed up your iterative algorithm, because there are so many different data structures and so many different queries, and only a few of them can actually help you speed up your algorithm. So here is the concrete math definition, given some endpoints set in RD, and say we are allow some pre-processing on P. And the reason why we are allowed to do some pre-processing, because usually optimization algorithm takes a lot of number of iterations. And so if we amortize the initial time to each iteration, it is very cheap. So therefore, we don't need to worry about it if we spend too much on pre-processing. And next question is, what are the queries we need to solve our problem? And here is one possible query, which is very standard in nearest neighbor search literature. And for any query point Q, and you have some parameter alpha, which between 0 and 1, and we can find a P prime in P, such that P prime inner product with Q is at least alpha times the best inner product P comma Q. And for our application, sometimes we also need such kind of query, which is list query. Like I give you a query, I give you a query point Q, and also a parameter tau, and you want to list all the points in this data set such that the inner product at least tau. So there are a number of data structures you can use, and they have different like pre-process time and query time and space, and also different error and different probability. So you need to very carefully choose which one you want to use to analyze your like iterative algorithm. So instead of using like a high dimension German search, and people in practical they are using like something called like locality sensitive hashing, and locality sensitive hashing also has some theoretical guarantees, which could be used for some other applications of iterative algorithm. So similarly, and such data structure also exists for the furthest neighbor search by Indic 2002 paper. And however, like for the first neighbor search, we don't know too much application. Therefore, this data structure is less studied than like nearest search. So the rest of talk I will focus on like how to use the idea to speed up deep learning. So deep learning has many applications. For example, image classification, NLP, and health and medical data, and also playing games. And also one of the ultimate goals of using deep learning is to like design automatic driving system. Of course, like deep learning is one of the like most important hammer in this century. So a lot of like a deep learning practical like a result, there is no like a theory intuition. And one of my research, I want to like focus on like building a theory intuition for this like a practical tool. So for example, one particular question I'm interested in how fast can we train a neural network? So basically the idea of this, the idea behind the theory of this talk is actually from some very practical algorithm in training neural net in practice. So I will first like survey some like existing known results, convergence results for deep learning. So usually like they assume like some assumption like this. The first one, the neural network is sufficiently large, like sufficiently wide, because like if you say like M is the number of neurons in each layer of a neural network, and as long as M is like a bigger than polynomial of all the other parameters, for example, like number of points, number of pixels, number of layers, all the separation between data, then we can hope like we can train a neural network and convert to some good global minimum. Another like assumption called like input data points are separable. And for example, like for any two input data points, you hope like for any two images, you hope like there is a gap between them. So this is true like if you look at our real life image or like ImageNet or any different data set. So the reason why you can assume, another reason why you can assume this assumption is if there are some like images, they have two like exact same like image, but their label are different, you cannot learn basically. So therefore you should like remove the exact same image from the data set before you run your training algorithm. And both of these two assumptions, they are very mild and acceptable for like practical people. And these two assumptions also called like known as like an NTK theory. And so the NTK theory is saying the following: like you're like we are running like a linear regression, and you can also run a kernel regression. And NTK is saying like a neural network basically doing some kernel regression where a kernel has some particular form like this. So for any like a two data point x and xj, and you can define a kernel to be the expectation over a random Gaussian w, which is w is simple from random Gaussian, and your when scalar is become like xi transpose times xj times the indicator between the xi w and xj w. So this NTK theory is very popular in the field of machine learning over the last few years, and there are so many papers based on this NTK theory. And there is one interesting paper, and they actually could connect the input data points are separable with this NTK theory. Basically, they can show like if your data are delta separable, for example, any two data points and delta gap, then the minimum eigenvalue of your kernel is at least delta over n squared. So basically, the overall, this theory is saying like if you're starting from random initialization, then with high probability either GD or SGD is going to find the W, such that like LW, the loss at W, at this W as most epsilon, and you will pay like a log only iteration. Here, like yeah.
Yeah, just out of curiosity, that kernel function, it's not just like the inner product of x and I times like something like the cosine or sine of the angle?
Oh yeah, you can. So yeah, that's a very good question. So you can turn this one to be cosine, and but you need to assume like all the xi and xj they are on unit sphere. Then you can do that.
Okay. All right.
Yeah, actually, when we analyze the kernel, we actually assume that because when people are training like a real like a machine learning like an image, they actually normalize all the image to like a unit sphere. Otherwise, you will have some like issue about gradient exploding or vanishing in practice. Yeah, that's a very good question. So this is a very like a high level theory. I omit many like parameter details in the theory. And the major message of this theory is saying like if you have like enough parameters, and then like greedy type of training algorithm will allow like a deep neural network to memorize the input data. So there are a lot of works like they are either based on the input data separable assumption, or they are based on like the eigenvalue like of neural tangent kernel assumptions based on OS 20 paper, and all these works are online together. So here I will briefly tell you our techniques. So usually optimization algorithm boils down to an iterative algorithm, and you have T iterations, and every iteration you need to involve like many like a heavy like a numerical linear computation, and for example matrix vector multiplication or matrix dimension multiplication or matrix inversion. The major question here is how to turn this algebra computations into a search question, and then we can probably apply nearest neighbor search in each iteration, and we can actually do the fast computation. So now I will give you some very basic setup of one hidden layer neural network. And say like f is a neural network function, and f of x here is just one image, and this m is the width of neural network, and the wr is the width between the input layer and the hidden layer, and ar is the weight between the hidden layer and output layer. So wr is a vector in rd, and ar is a vector in scale. It's just a scalar. And the phi here is a nonlinear acting function in neural network. In practice, we choose phi to be ReLU or like a sigmoid function. The ReLU just takes the maximum between the input entry and 0. So in this talk, I will just focus on ReLU. So let's say we have n number of data points, and d is data dimension. In practice, d is just like the number of pixels in an image, and m is the width of neural network, and capital T is the number of iterations. So let's say like say is the input size of parameter. So in this like setting, the input size is going to be the number of points plus the parameter of neural network. So we have like n input data points. So therefore like the number of input points takes like nd size, and the parameter of neural network takes md, because like the most expensive thing is to store a w, and w is m by d matrix. As you can see from this like a basic calculation, the input size of this problem is actually like is nd plus md. However, like one like a naive observation is if you want to evaluate endpoints for this function, like because for every point you want to compute this function fxi, and it will take like m times d time. And if you want to evaluate endpoints, and you actually need to like have to spend like omega m and d time. So think of you have some greedy algorithm, like even at every iteration, you want to evaluate this function f, you want to evaluate how like good their neural network performance, and you already take like capital T times m and d time. And the goal of this talk is we are going to show like how to like improve this m and d time to some small of m and d by using like some data structure called like nearest neighbor search. So another important like thing to force like our neural network analysis go through and to support of like a nearest neighbor data structure, we also need to modify the neural tangent kernel. Like instead of using ReLU, we are going to use some like shifted version of ReLU, which is going to take the minus b, the b is the shifted value. And we can also show a connection between the separability and the smallest eigenvalue of shifted NTK. For example, like the classical NTK is just a corresponding version where b is 0, And here we are going to choose some b to be something bigger than 0. And then you can see like in the connection between eigenvalue and the separate beta, you will lose some exponent in the minus b squared. So eventually in the algorithm, we are going to choose like a b to be like theta root log m. So as you can see from this bound, like for b equal to 0, it matches the OS20 paper. And for b goes to infinity, and the indicator function will always output 0. So therefore, like the entire kernel function will just be 0 forever. So therefore, the minimum eigenvalue is also 0. So it's also match some intuition. So here, like our like a speed up result, like we're given like endpoints, and like you have like d-dimension space, in d-dimension space, and say that your neural network has m neurons, and we are going to spend like O of like m log m time, sorry, on preprocessing the initial weights of neural network. So preprocessing initial weights is actually very like standard in like practical machine learning training, because when they want to train a neural network, they are not like trying to train from scratch. They actually download some neural network. Actually, the weights actually preprocessed by some Google or some Facebook software already. So if we process the initial weight, we can build a dynamic data structure, which is neighbor search data structure. Then like if you run like a GD algorithm, and you just run the same algorithm as the previous, all the previous work, and you can get a slight improvement by like, instead of getting m, you can get m to the 1 minus 1 over d. So as you can see, like when d is super large, this improved very tiny. But for like some constant d, you do get some improvement in theory. So this idea is known, like it has been widely used in practice, but this is the first work we can show, like we can prove something in theory. We also have another result, like which is slightly better. And instead of preprocessing like all the like the weights, we are going to just preprocess input data points. This is also very natural, like in practice, because the ImageNet data set, they are just there. And whenever people want to train their neural network, they always use the neural network pre-trained on like the ImageNet. So you can definitely like preprocess the ImageNet better. And in this case, we will build a static data structure. And eventually, like we are going to give algorithm, which instead of like getting slightly improvement, we can get like some like a 1 over 5 improvement for any like d even. So in the talk, I will focus on like speed up result for the first part, and we should build a dynamic like nearest neighbor search data structure on weights. So here I will tell you the challenge, like why like a bypass that's all of like NMD like barrier is very hard in practice is in theory. So like for each data xi in RD, if you want to compute like f of xi, like even exactly, you have to take like MD time. But if you want to only like compute approximately, we call like phi of z some ReLU. And then the observation is only a few neurons will be very important, like when you compute them. Like say like SI a set of important neurons, and their inner product will be huge, like for example, at least epsilon. And for the rest, their inner product may be 0. And in this case, you can look at this like a network. And for the weight W1, you connect from all the input layer to the first node in the hidden layer, and you can compute the inner product. And the light green color denote like we are not the value is very small. We are not active neuron. And the dark green color denotes the case we are going to active neuron. And once you check all the neurons, you will know like which are the neurons you are active and which are the neurons you are not active. And eventually, like say your SI just a set of side 2, and you just active neuron 2 and neuron M, then you can compute a final prediction. So, but this algorithm is very naive because I'm checking all the neurons. And once you check all the neurons, of course, you know which neuron is active, which neuron is not active. But this already spanned like NMD space. So the major issue like we need to overcome here is we want to figure out a set of like important or active neurons without looking at each of them, like in sublinear in like MD time. So like how do we figure out this important set Si in sublinear time? So what we do is we are going to precise all the weights, and we can build a nearest neighbor search data structure on this like weights. And now like we are going to like use like a nearest neighbor search query, like instead of, because our data structure is based on weights, and then our query is based on image. So you can also build data structure or image and then your query is weights. So here, let's say, if you query a particular image and we are going to figure out a bunch of important neurons for you, like say like we choose k equal to 5, and then for this image, we are going to tell you S1 is this one. And for another neuron, like it will tell you a different, for another image, you will tell you a different set. And you can query different images, and the major intuition for every image, like only like a few number of neurons are going to be active. And this is not enough. Like in every iteration, we still need to make sure like the WT plus 1 change from WT is very small. Because if they are changing a lot, we need to rebuild the data structure. And if they only change a little bit, we can actually do some dynamic update of this like data structure. So in addition, like in order to like make sure like the delta W like the original like NTK analysis is only guaranteeing like the L2 normal delta W is small. Instead, in order to use like the near search data structure, their error is very like fragile, it's very hard to broken. So you need to make sure like the L0 norm of the delta W is very small. So therefore, we need to modify the NTK or classical NTK form to like shifted NTK to make sure like the number of neurons like only active a little is small. Like, but this is still like enough for you to show the convergence result.
Zhao?
Yeah.
So the nearest neighbor, just to understand here, you have some, okay, input image X, and then we're asking for, let's say, like the W's that are closest to the representation of X?
Yeah.
Okay, so all the weight vectors that are somehow close.
Yeah, you basically look at the maximum inner products. Instead of doing near, you can see it's more like because L2 nearest neighbor search is equivalent to maximum inner product.
Yeah.
So in the problem we care is actually inner product, and to translate the L2 norm like a nearest neighbor search with to the like inner product search, you need to assume all the data points they are on units for. Otherwise, this will not work.
And if you only return like the top K, I don't know, nearest neighbors, you were saying that you need to have a good guarantee that no more than K neurons will get activated?
Yeah. So yeah, that's because like because in this analysis, like this optimization analysis, where like it's very different from other like using like a sketching or maintenance or sampling. You can hope like expectation correct and the variance is small. And here, if you miss one neuron, you are just completely dead. There is no way to fix the analysis. At least I don't know how to fix analysis. So therefore, you have to promise like the number of changes are very small and the negative activations are also very small. Then you just I think in our application we choose K to be like M to the like 0.2 somehow, something like this. Yeah, some linear M. Yeah.
Thanks.
Any other questions? Okay. In the next few slides, I will briefly tell you some applications, and so our idea like also can be combined with some like a quantum like a group search, and therefore you can get some quantum algorithm. And the interesting part is that you want to use the quantum algorithm, you can actually bypass like this preprocessing. You don't need to spend any time in preprocessing. You just run the group search online. And you can get the exact same time, but you don't need to spend any time on preprocessing. And another application is we can apply this idea like to like Frank-Wolf algorithm. So usually Frank-Wolf algorithm can be summarized in 2 steps. The first step, you are given a gradient, and you want to find a vector in feasible domain that has a maximum inner product. Because you are trying to like do an inner product search, that's why you can use it. And then you update the current weight with the retrieved vector. So here is a concrete math equation. You are trying to find ST, which is argmin of like small s in capital S. And you basically look at their inner product. And this capital S is a discrete set. Therefore, you can preprocess it as S and to build a data structure for you. And whenever you see some like you find some ST, you just update the weights, and update time is very cheap. And therefore, you can also get some like a similar result for like from fork algorithm speed up using this nearest research data structure. But here, this analysis is easier to handle. You don't need to get like exact like top K or something, because you only want to find the minimum one. So therefore, you can use like you don't need to use like high dimensions search data structure. You can just use local distance hashing. That's already very good. And the interesting part is like we are not the first one to use this algorithm. People already try to use this idea in practice, but they don't know how to prove any guarantee. We are the first one to prove some guarantee. So, and also this idea can be used in some regime of the reinforcement learning where the action space is super huge. And if your naive implementation need to linear scan of the entire action space to find the best action, and using our data structure, you only need to find the approximate good one, and then like the algorithm still can converge. So another like a direction is like is very different from previous application, which is instead for discriminant questions, and instead of using nearest neighbor search, and the right thing you should use is called something like a furthest neighbor search. And the intuition is kind of hard to plan. Like if you are interested in this area, you can ask me. We can chat offline, or you can email me. So we are going to using like the data structure. We can significantly speed up the running time of many discrete questions. So here I just give you one application, and which is called a one-set container. So as everyone knows, the container problem is very hard to get a polynomial time. At least we don't know how to get any polynomial time. But for one-set container, Weaver has a result like he can show like in some polynomial time, like for example, mn time. So in here, like we can actually use the first neighbor data structure to speed up this mn to be like m to the 1.01. So single like m equal to in the case, like we are all going to take m squared, but we are almost take just a near linear time. Yeah, that's all for today's talk. Sorry for late for 1 minute, and if you have any questions, you can ask me.